Okay, and I guess the idea was I would know where the
Yeah,
is this time. Okay, so
just to avoid distortion, I will mute it here. Okay,
some message.
somebody's trying to enter.
Admit somebody.
Yeah, I will take care from my phone
Okay.
for people, new
Oh,
people.
okay,
that-
that's good. Yeah.
Oh.
Okay.
I don't know why he's not appearing because I permitted. That is correct. Oh yeah.
Okay, so he
Oh, yeah.
said something. Hello, Stephen. My.
Yeah.
Okay.
Boa tarde, João. Bem-vindo. Eu acho que não tá tendo
E aí,
interferência.
Josnei, boa tarde.
Boa tarde, tudo bem? Agora não vai ter mais interferência. A gente já vai começar. So we'll start brief soon. I think we can get started because if somebody appears, they always can record later and watch the.
Also be up for a few minutes at least.
Okay, so feel free to take it over from where you start. Yes.
Okay, thank you. So we're continuing from where we were last time. Well, remember, we went over a few basic concepts of algebraic geometry, and we learned what it meant to resolve what a singularity was. And today what we're going to do is we're aware of the fact now that we can have singularities. And one of the nice things about non-singular things is that they're locally UFDs. So if you have if you're in a surface and if you have a curve, you can find one equation which will describe it. Well, the singularity that can't be done, that it gets to be very complicated. So today we're going to start by learning what it means to resolve singularities. In other words, some simple algebraic process, if it exists, which allows you to smooth out all the singularities and end up with something non-singular. So I'll start out by giving an example, a definition of what this means. And then I will just tell you what the different terms in it mean. Okay, so this is the definition. Let's suppose that X is a scheme. So what is a resolution of singularities? Of singularities of X is a, okay, these are words I'm going to tell you what they mean. It's a proper birational morphism phi from Y to X, such that Y is a non-singular scheme. Okay. Can everybody read what I've written? Is it big enough? Any interaction here? I don't know. Probably not.
Yeah, nobody said,
there's something here. I can read it. Thank you. Okay. Thank you, Stephen. Okay. And also, yes. And can you hear me? Can everyone hear me? Okay, that's good. Oh, there's someone else I think needs to be admitted. I guess the permittier.
Yeah.
I said that.
Yeah.
Okay, thank you. I guess if that comes up, I can just press that button.
Yes.
Okay. Hello, Shrishti. Okay. So this is, what do some of these words mean? The first one is that, what does it mean to be a morphism? if for every point of alpha in Y, there exist affine neighborhoods on U of U is equal to spec of A.
I'll take it.
Sorry, yeah. I guess if we run into trouble that we'll do something. U is equal to spec A of alpha and B equals spec of B of beta is equal to phi of alpha. I hope is this legible? It's getting a little difficult, I know. Okay, so I'm going to have to unfortunately erase this part of it. So we have a morphism which resolves singularities, and I'm going to tell you what the different words mean. Okay, so. Okay, and V of beta in Y, a neighbor U of alpha in Y, and this should be in X, but such that, okay, the phi of U is contained in V, and this and phi is U to V is the map F sharp from spec of A to spec of B, which is the F star. Well, I'll just write it like this. It's a prime P goes to the pre-image of P, where F maps B into A is a ring homomorphism. Okay, so that's how you construct this. So somehow globally it's some complicated thing, but you understand it locally. It's all in terms of the local structure of the ring. So in general, for instance, maybe these will all be over a field K. These will be K algebra homomorphism. F will be a K algebra homomorphism. Okay, so that's what it means to be a morphism. So locally, it has this nice description, and then you patch them together somehow. Okay. Okay, so then the next word we need to learn is what it means to be birational. So we say that y from y to x is birational if there exists an open dense subset U of y of x, U of x such that the pre-image of U to U is an isomorphism. So in general, what one would like best to do is to take U just to be the open set of non-singular points. And then you would like to have this be an isomorphism there. And finally, what does it mean to be proper? Phi is proper if for every valuation ring if V with morphism from the spectrum of V into X, there is a unique morphism beta, maybe I shouldn't, well, from alpha, there's a unique morphism beta from spec D into Y such that phi composed with beta is equal to alpha. And I'll draw a picture of this in a moment. But one of the things this tells you that the map is always surjective. Okay, so in particular, you cannot resolve singularities by just removing a point. So removing a point. Okay, so this is some generalization of well, a map that, like, from a compact topological space to another space. That's a proper morphism, and it's something like that. Okay, so now let's say something about when these resolutions exist. Okay, so the first thing is that resolution of singularities do not exist for arbitrary schemes. Okay, and the first thing that you see, there's a rather naive thing that goes wrong, is that X must be reduced, or at least generically reduced, which means that the structure sheet for the X is has no nilpotence in it. And also there's more subtle examples. There's, for instance, Nagata is most famous for a series of counterexamples he gave. And one of them was that to show that there exists a local domain. So it's certainly reduced R, such that, and it's Noetherian, such that must be reduced, maybe I should say N Noetherian. Okay, they're such that which is equal to the M-adic completion. It's not reduced. So this implies that we cannot have a resolution of spec R. It's not possible. So the M-adic completion, say if R is a polynomial ring modulo an ideal, the completion is to replace the polynomial ring with the power series ring, and then you just mod out by the I in that ring. Okay, so it is in fact the usual kind of rings that come up in algebra or in number theory. This kind of bad phenomena cannot happen. You could take a domain, and maybe it's not a domain anymore, but it will at least be reduced. You won't pick up any of these nilpotents. Okay, so basically there's a conjecture, which is essentially for the weakest assumptions where it can exist, which include things like it has to behave well under completion, that it's will always exist. So and this is conjectured that resolution of singularities exist for reduced excellent schemes. Okay, so this concept of excellence seems to be something which maybe Growth Indeed came up with after being familiar with Hironaka's work on resolution singularities. What it sort of points to the minimum conditions you can have to make things work. And so, in other words, you have to describe some category which is rules out examples, strange examples like this. Okay, but this includes finite type schemes over, maybe I should say, reduced schemes over a field and over Z. So examples of this is going to be something like spec A adjoin x1, xn modulo semi-field I. Locally, it'll look like this, where radical of I is equal to f, an element of R, such that f to the n in R for some n, that this is equal to I. That's the reduced condition. And with A is equal to a field or Z. Okay, so also that'll be stable under things like taking completions. So basically, you get most of the things which come up in algebraic geometry and in number theory, or actually all the things which are the basic objects of study. And also this extends to complex analytic spaces, which was done by Hironaka himself. And that they have the property that you have to be a little careful about defining these things, but always the local rings of points on analytic spaces are excellent. They're Noetherian and excellent. So one can do this. Okay, so what is known? The great theorem on this is it's conjectured. So since I phrased it this way, that you can see that it's not completely known. So let's talk about what is known. And there's been a really, I guess that if you wanted to, you could say that Newton knew how to resolve plane singularities. In fact, in some sense, the best proof is by Newton. And he didn't really phrase it that way, and I'm not sure he was looking at it that way. For surfaces, it was done maybe in the late 19th century and early part of the 20th century, but there are some issues with the proofs. Zariski wrote in the late 20s some account of this, and apparently it was while going through studying these proofs and figuring out what was wrong with them that he decided that all of algebraic geometry had to be redone and with proper rigor and foundations. But it's very interesting reading the accounts because of Zariski, because he explains all these beautiful geometric ideas, and then he points out why the proof doesn't quite work, what's missing. Okay, so finally it was in the 30s that dimension 2 was solved, resolution for surfaces over the complex numbers or over a field of characteristic 0. And one of the first proofs was by Zariski. Okay, but the really great result, which is that the theorem of Hironaka, which I think was published in 1964, and he was awarded the Fields Medal for this, that resolution of singularities is true for reduced excellent schemes containing over a field of characteristic zero. Okay, so for instance, things like this, where A is a field of characteristic zero. Okay, and I guess a paper appeared, or there were two long papers, which appeared in this time. He didn't quite get this for completely general excellent schemes, although he did prove it over an excellent local ring. And then he proved it for later on. Then he used that was enough, since the field is excellent, for him to deduce it in the case of algebraic geometry. And after that time, Hironaka didn't really properly publish many things. He wrote a lot of lecture notes. He seemed to have had a very good time visiting his friends in Spain and France and Italy. And there were some sort of very rough notes that have been written up, which are generally very hard to even get copies of. But along the way, he actually made a lot of improvements and simplifications in this. And this led to work by some other people in recent decades, going up to now. The main thing, like names like Bierstone and Millman and Orlando Villamayor. And one of the great ideas was to actually try to write out a proof that anybody could understand who knew a little algebraic geometry without spending years working on it. And also that Michael Temkin has recently, he's proven it for all excellent schemes where it's gone that far. And so that's a little bit of a generalization. Okay, so what one of the jokes is that after getting his Fields Medal in Japan, it was a tradition for people to have a meeting with their emperor, who was an educated man, that he had some degree in chemistry. So when meeting with him, I guess the tradition was the advisor of the guy who got the big prestigious international award, like the Fields Medal, to also make the appearance with the guy who got the award. And in this case, actually, Hironaka was the student of Zariski, but before leaving, going to Harvard, that he was a student studied under Nagata, who was mentioned here, was another great mathematician. So Nagata went with him when he met with the emperor, and apparently the emperor asked him, "What about characteristic P?" So I guess obviously Nagata had prepared him for this, but it does say something about the sophistication of the emperor, I think, that you would actually do this. But apparently the Hironaka actually took this very seriously, I guess, and he's still now working on trying to prove it in characteristic P. So it's an ongoing story. But what is known about characteristic P? There's that wherever it's known over fields of characteristic P, at this point, everything's known. So in fact, if X is an excellent reduced scheme of dimension less than or equal to 3, then resolution holds. Okay, and in fact, about this time, I guess his proof of this appeared a couple of years later, but Avianca proved this over algebraically closed field, a characteristic greater than or equal to 5. And since then, the progress has been fairly recently that to get it to this full case of the I'm good. What? I'm good at. Let's see. It's 3 factorial is 6. It has to be bigger than 6. So I guess not. It's 7.
Yeah.
7 in height. You're right. Okay, 7 in height. So even though he told me personally that he knew how to do, he had worked out 5, 3, and 2, but the proof was so long and complicated that he just put it in his drawer and didn't try publishing them, especially the case 2, b equals 2. Okay, but anyway, there's other things to do too to get to the general case. But unquestionably, the proof, which is quite recent by Kozar and Pilton doing the general case, that it did make use of some of Abjanker's methods, and they had a lot of original ideas of their own, and it's a very long proof. Okay, so in fact, there seems to be some key missing in order to go on, and indeed, who knows? Maybe it's not even true, but this is where things are. Okay, well, related to this is another problem, which I will tell you about, which is local uniformization.
I guess to give a dimension, right? The concept is done to add all the articles, it's easily over 500 pages, right?
It's something like that. Yeah, I think actually they sort of have two generations of proofs, and I think you can more or less ignore the first 200 or 300 pages and read the second one. But yeah, even the second one is several hundred pages long. It's really quite overwhelming. And some of the proof is rather, especially the part that comes from Abjanker's work is rather conceptual. But there's sort of one case. It's an Art and Schreier extension. If that is the only case, and this is a couple of hundred pages of them to prove this using ad hoc methods, really. So it's really very very difficult. But anyway, it's a good problem to work on. Okay, so let's talk now about a related problem called local uniformization, which was in fact formulated by Zariski. So let's suppose that that R is an excellent local domain. Remember, this is effectively the most general case. We can hope this to be true with some quotient field K and take evaluation of K, which dominates R. Okay, so in other words, we're given an inclusion here into the valuation ring of nu. These are the elements which have positive value, or not. Sorry, they have non-negative value in the field. Okay, so this is okay. So then what is a local uniformization? A local uniformization of R along nu is an extension like this. R to S and then to OB, such that R to S is essentially a finite type. I'll tell you what that means. And is regular. Okay, so what does this essentially finite type means? This means that S is a polynomial ring over R modulo a prime ideal, and then you localize that at some prime ideal. Okay, that's what it means in this case. And it's a regular local ring. Okay, so how is this related? Well, remember when we were talking about this properness condition, these valuation rings play a role. So somehow where the idea is, and why Zariski introduced this concept, was he was interested in resolving surface singularities initially. And the idea is that you can do some process, some sort of blowing up, which we'll describe what that is. Okay, so you blow up a point, and then, well, there may be some point up there where it's still singular. You blow it up, and there's some process called normalization where you end up with only a finite number of singular points. So you do this, and then you blow those points up again, normalize only finitely many singular points, and then you keep iterating this, and hopefully you'll end up with something eventually that's non-singular. But what happens if you don't? Well, that means you have this infinite chain of points where you just keep blowing up, and then you get all of these points where it's always singular. And that determines a valuation ring. If you take the union of all of those local rings with the singular points, that will be a valuation ring. So what the idea is that, well, at least you can see from this algorithm, if you apply this algorithm in dimension 2, that the obstruction to resolving singularities will be overcome if you can perform local uniformization. So that's where this idea came from, and it's actually what you can see from this argument is that the resolution of singularities, a global resolution of singularities will imply local uniformization, but generally not the other way around. Although Zariski had a very brilliant argument which shows that if you, in dimension less than or equal to 3, local uniformization actually does imply global resolution of singularities, because you can find a finite number of charts which are non-singular from this method. And then the problem is patching them together nicely. And this is possible to do by his argument in dimension less than or equal to 3, but no one's made any success in going beyond that. So that's, yeah.
Maybe it's worth to say that they're reducing to finitely many. This is done by the compactness of the spectrum.
Right, right. So that in itself is a non-trivial statement, of course. Yeah. That's right.
The difficulty is the patching the finitely many, right?
Right, that's the thing. And if you're happy with something which is like, well, if you're in complex topology, it would be non-Hausdorff. If you're okay with something like that, they say it's not separated, then you can easily do it. But the problem is getting something which is sort of a respectable space while you're at it. So, and this people don't know how to do, except for in low dimensions. Okay, so let me tell you about this. This is, I'll call this a proposition. It's a resolution of singularities. Certainly that always implies local uniformization. So even in higher dimension, that if you can do local uniformization, you're off to a good start in proving resolution of singularities. Okay, so let's look at our situation here. This is the proof. Okay, so let's let nu be a valuation ring. Okay, and we want to resolve along it, dominating R. And then we have a picture like this. Then that means that the map on spaces is in the opposite direction. So we have a map from the spectrum of this valuation ring into the affine ring spec of R. And then here's a resolution of singularities. So this is a resolution of singularities. Okay, so by the properness, this is proper. So we know that there exists a map like this. In fact, it has to be a unique map like this from the properties. Okay, so I'll call this lambda. And then what do we have then? We then look at what happens on the level of algebra here. Okay, remember that these maps of schemes are locally, morphisms of schemes are locally come from homomorphisms of rings. So we have R, and then the map pi becomes pi star, and then this, let me write it like this. This becomes pi star, and then this goes to the local ring of this point over here, lambda of the of this map over here. MV is the maximal ideal of this, and then this goes by lambda star to OV. Okay, and this was your original map that we're given over here. So we have this, and this here is regular. It's a regular local ring, since this is a resolution of singularity. So this solves the problem. But you see that all of these kind of global issues are not addressed in this. Okay, and then there's a theorem that, and this was proven by Drisky in the 1940s. And this was, maybe the paper appeared in 1944. And this was about 20 years before Hironaka, his student Hironaka's proof of the general theorem of resolution, which is that if X is an algebraic variety of characteristic 0, then local uniformization holds above X. So in other words, if you take the local ring of a point on X, and that means that the local uniformization holds above it. Okay, and then also that from Abjanker, and this was in the maybe 1966, and the Kozar Pilton within the last few years, that the local uniformization holds for excellent local domains, at least reduced schemes of dimension less than equal to 3. Okay, and in fact, this is one sort of interesting thing about this is that it turns out actually that there is sort of an idea coming in here called, in Zariski's work, where it's essentially a what is a hypersurface of maximal contact, and I tell you what that is. But it turns out that's something special about characteristic 0. We'll learn more about that. Doesn't exist in characteristic P positive characteristic, which one of Abjanker's students, Nara Seaman, showed. And because of this, it's much, much harder in these lower dimensions. But all of the proofs of resolution of dimension 3 use local uniformization, where they first prove it. And this is in spite of the fact that the whole thing is much, much more complicated in characteristic P than it is of the whole valuation theory. It's much more complicated in characteristic P than it is in characteristic 0. Okay, so with that, let's go back now and talk a little bit more about the machinery. So I've been talking about blowing up points and things like that. And of course, we're saying, okay, you want to find a proper birational morphism, but what is that? So in fact, this was something that historically algebraic geometers, the way they constructed maps was they take something in one projective space and then they project it down to another projective space. So you use some linear transformation. And the idea is that you can get any kind of map you want by embedding it properly in a projective space. Okay, that's in fact, that's what a so-called projective morphism is. And a proper morphism is almost a projective morphism. And in fact, I think in practice, whenever anybody resolves singularities, they do it by a proper morphism. But the problem is that this is just too coarse a concept for something as delicate as this resolution of singularities. And starting with Zariski and then going on to Hironaka, they worked out a very general theory of how to approach this problem by blowing up ideals. Okay, so let me tell you what this is, and then when we're going to look at it then in a very specific case of blowing up points on the surface, and we will then resolve plane curve singularities, which contain already many of the ideas in the subject. So to begin with, let's learn what it means to blow up of an ideal. Okay, so let's suppose that X is a scheme, and we have I contained in OX is an ideal sheaf. Okay, so what does this mean? Basically, what this means is, okay, this is some geometric object, but locally it's covered by these affine things. So an ideal sheaf means it's something that, well, when you restrict to the affine guy, that this ring is just an ideal in the ring. But somehow you have to patch these things all together, and that gives you this concept of an ideal sheaf. So you write it as a script I instead of just a Roman I. Okay. So what is the blow up of I is I from B is equal to B of I to X. And this is equal to the proj of the direct sum n bigger and equal to 0 I to the n. Okay, so what is this object? This is an object in algebraic geometry which is fairly simple locally. So in fact, if you take an affine open subset U, we take U is equal to an affine spec of R. It's an affine open subset of X, and we restrict to this, then pi inverse U is just going to be equal to the blow up of an ideal I, which is equal to the proj of direct sum n bigger and equal to 0 I to the n, where I is the language the geometers use is this one. This is really what happens when you restrict the sheaf I to this ring R. Okay, so it has this rather simple form, or at least simpler form. So what is this thing? In fact, that this is actually the Riesz ring of the ideal, and this is important in commutative algebra, although for the most part, they don't seem to think of it in this context. I think it may be that they define this, Riesz defined this before Hironaka, but I'm not sure. But some of the things they work with this in commutative algebra are somewhat geometric, but they seem not to have really been looking at it quite this way. But Ries is always difficult if you look at his beautiful work, that he knows a lot more than he lets on. So he may have had some idea of this. So, okay, what is this? Well, there's a nice description of this, that if I is equal to F1 up to Fm, those are generators for the ideal, then you can, following the general principle, remember we learned the proj is a set of homogeneous primes in this ring, and this is actually has an affine cover of the spectrums, which at least are a little less difficult when we look at this. So really, you can think of this in the sense of localization of the dividing. You localize at Fi, and then you look at this. Or if R is a domain, for instance, then there's no trouble. These are just elements of the quotient field. Okay, so this is something that's at least rather concrete that one can work with. Although, of course, actually saying what in the world this thing really, the structure of it is not easy, except for in some very simple cases. Okay, so there's another construction that one needs for this. Let's suppose that W is contained in X, is a subscheme, is a closed subscheme. With its own ideal sheaf, IW on X. Okay, so in other words, this means that in the language of algebraic geometry, W is spec of OX mod IW. Okay, so locally, if you restrict to an affine, then you take the local ring R, the ring R, and then you mod out by the ideal defining it. Okay, so the total transform of W W is just the preimage of W. So this is the subscheme. Well, is this is going to, I'll just write it like this. This is the spec of O BI. Then you mod out by, in fact, the IW times O BI. Okay, so you just take everything, the set theoretically, you're just looking at everything above W. But the structure of this ring could be really terrible. Set theoretically, the structure of this ring, one has that pi inverse of W is equal to the pi star of W. But in this case, you've got some more structure which you're looking at. You're looking at this thing. Okay, so now let's let U is equal to X minus V of VI. So this is where the support of I, and this is a closed set, so that from this, if you look at the definition, one has pi inverse U to U is an isomorphism. Okay, so it's and strict transform. So we have this, and in fact, that we won't do this, but we can show that pi is actually, pi is proper. Okay, and this is, was proven by Cutkosky. And I've erased these forms, but it's a rather ingenious argument that you make because of the fact that in one of those charts has to be contained, where you divide successfully by the different f of i's, one of them has to be contained in the valuation ring. Okay, so there's a little more here. I'll say that the strict transform of W tilde of W is the Zariski closure of the preimage of this in the blow-up of I. So remember, over U, it's an isomorphism, but then you make the closure in here. And in fact, the way you do this is by you take this ideal here and you remove everything you can. Like there may be some extra components in the preimage here, which will show up in this structure, this ideal, and you need to get rid of them. And I won't go into that now, but you use this using a colon idea.
Might be better, no?
Yeah, I know it's getting kind of hard to see, so hopefully let's see if this works better. Yeah, that does seem to work better. Okay, that's good. Okay, thank you. Yeah, that looks better. Hopefully this could be read what I've done.
So some time ago, somebody asked a question. I just see it now. So
Okay.
regarding the characteristic PKs, just to be sure I understand, the restriction on the characteristic is for dimension 3, right? No
That's where
restriction for
where it's known, yeah.
Yeah. So no restrictions for dimension 1 or 2.
Or 3. For that in dimension less than or equal to 3, resolution is known in over any field. But in dimension bigger than 3, 4, 5, so on, it's only known in characteristic 0.
But I think this was a longer time ago when you were talking about this greater or equal to 5. That was
that's a
before.
characteristic, yeah.
Yeah. So that was before.
Or greater than 5, I guess.
Yeah, greater than 5. That was for dimension 3.
But that was in the 60s.
In the 60s until Kossar-Piltan. Kossar-Piltan has no restrictions even in dimension 3, right?
That's correct.
Okay.
Yeah, they have no restriction of any kind. So the most general statement you can get.
Okay. Sorry for the delay.
Okay. Yeah. Thank you for looking at this. Yeah. Okay. So now let's look up. Let's consider an important case, which is the motivating case for all this. So what we're embarking on now is to prove resolution of singularities for a curve inside a plane. Okay, which is already a bit challenging and contains important ideas. Contains important ideas for the general proof, but which is of course much more difficult. So the first thing to do is, okay, we looked at this blowing up in a very abstract situation, but let's look at specifically blowing up a point P in the plane over K, and one models that as the spectrum of K of xy. Remember that since K is algebraically closed, there's a one-to-one correspondence between actual points in the plane, K2, and maximal ideals in here. So given a point AB here, the corresponding maximal ideal is generated by x minus A and y minus B. Okay, so we have P. One can say that the ideal of the point P is, which I can think of as say A, B, is in K2, is just X minus A, Y minus B, which is contained in K adjoin XY. So we use this, this identification. So after making a change of variables, variables, well, this one works better. So I'll use this. That works much better. Making a change of variables. Replacing X with X minus A and Y with Y minus B. We may assume that P is the origin. So then the ideal then, maximal ideal is just going to be X and Y. So since we're thinking of this in this,
The way to A2K is not the spec, right? It's the spec M, the maximal ideal, right? Because I could have prime ideals that do not correspond to close points, right?
yeah, okay. So I didn't want to say this blowing up a closed point.
Okay.
And I didn't want to make it too
bottom
technical.
line, then the quality is tricky, right?
Well, I guess I'm sort of abusing notation because on one level I'm being rather modern in the sense that I'm calling this a point.
Yeah.
Okay, so strictly speaking, I shouldn't have said that.
Yeah.
But I said that to hoping it might be a little clearer, but I might have made it more confusing.
No, it's just there's a quality on the third line that's kind of
This one,
no, the upper line.
this one.
Yeah.
Okay, so let me fix this. This is by definition what A2K is if you're in scheme theory. That's the way they define it.
Okay.
And then this
Yeah.
sentence shouldn't be said.
Okay. Okay.
Okay, and then so then I say this.
Yeah.
Okay. We assume that. Okay, so I won't do this. We assume that P is equal to XY. Like that. But the motivation behind this is that you can also think of this as being a model of the plane K2, and this would correspond to the origin in that plane. Okay. Okay, so now let's let pi from B, which dp into A2 be the blow up of the ideal P. Okay, so remember what we said about this is that this is an ideal with two generators. So this is going to be a union of two defined charts. It'll be spec of XY, adjoin X over Y, and then union spec of K of XY, Y over X. Okay, like that. That was the formula. This is the F1 and the F2. And you look at this, you can see that this is spec of K of Y, X over Y. X is Y times XY, so you can get rid of it. And this is equal to spec of K X Y over X. So you see this is just isomorphic to A2, and this is isomorphic to A2. So somehow when you blow this thing up, you end up getting something which is covered by two planes. Okay, so let's see what happens then when we let's analyze it a little further. So far so good. For instance, this is still regular. And then what happens when we multiply P times K of X, K of Y, X over Y? That's the first one of these guys. Well, you see, this becomes a principal ideal. This is K, Y, Y, X of Y. And Y is that, and this is since X is equal to, of course, Y times X over Y. So you see that that the ideal XY, you can throw away X because it's already a multiple of Y. So it becomes principal. And in fact, that's what blowing up an ideal does. It makes it locally principal ideal. That's what's accomplished. So this tells me that U1 intersection pi inverse P is equal to V of Y, which is actually a line on U1, which is isomorphic to A2. And then we see that P times K of Y, I think this should be X, Y over X, is equal to X once he's by the same type of argument. So we see that U2 intersection pi inverse P is equal to V of X, which is a line on U2. Okay, so that's the geometry is not so bad. And what we see from this, for instance, is that if I take the whole preimage of the maximal ideal, it's going to be a curve. So let me do this one, which is much better. Okay. Okay, so we can conclude from this that E is equal to the whole preimage of P as a curve. And in fact, we can even say what kind of a curve it is. But before doing that, let me make the comment that it's isomorphism everywhere else, that the blow up of P minus E to the X minus P is an isomorphism. So when you blow up, it's only in the support of the ideal where anything can change. Okay, so what you're really doing here is you're having this this E and this that the P, and this is B of P, and this is X. So here's the point P. So the idea is you replace a point P with this curve E, and we have here that that this E is the union of these two charts. So we in fact look a little bit more at this U1 intersection pi inverse P is equal to the spectrum of K, Y, X of Y, and then mod P, K, Y, X, Y. And we know this is just equal to Y, K, Y, X of Y. So you set Y is equal to 0 in this. This is just spec of K, X over Y. Okay, and you also can check the same kind of calculation shows that this is equal to spec of K, Y over X. Okay, so we know that E is the union of these two guys is equal to spectrum of K adjoin XY union spec of k of y over x. And remember last lecture, we talked about projective space. And we can recognize this as just being projective space P1. Okay, so this is a P1. And in fact, from a more classical point of view, that this is in fact, if K is C, this is just the Riemann sphere. And this is the classical way of looking at it, that you remember you take when you do complex analysis, you take a variable Z, which vanishes at the origin, that's X, Y. You get almost everything except for this one extra point you get when you compactify. And that has the coordinate 1 over Z, Z inverse. So this is exactly that situation. Okay, now let's look at this a little bit more. And look at the structure a little more. Let's suppose that Q is in the preimage of P is a closed point. I'll just say point, but it's we'll make it a closed point. That if Q is in U1, it has to be either in U1 or U2. Then Q is a maximal ideal of R1 equals K adjoint XY over Y, which contains the ideal P times R1, which is equal to, remember, Y times R1. Okay, so this tells me, since K is algebraically closed, that the ideal Q has to be of this special form. For some alpha in K. That you wouldn't have such a nice description if it's not algebraically closed, but since it's algebraically closed, one has a very nice description like this. Okay, so in fact, one can analyze the situation by setting set of y1 is equal to y, and x1 equals x y minus alpha, which are regular parameters at that point. And these are regular parameters, the generators of the maximal ideal of the regular local ring OVP localized at Q, which is just K adjoint X, Y, Y, and then we have to localize at Y, X, Y minus alpha. And the way you can understand this, and this is a more classical point of this, is you can see then that X is equal to Y1 times X1 plus alpha, and Y is Y1. Okay, so somehow that describes what this map is near Q, from the map projecting Q down to P. It's just this transformation like this, okay, which is something that one can work with more tangibly than this very abstract definition of what a blow-up is. Okay, so now we mentioned that that the only point on the Riemann sphere, that E, that you get from blowing up, which is not in U1, is this point at infinity. So that's the only other point that you can get that you need to be worried, you need to be concerned with. And I will say that. Okay, so basically with alpha can be anything in K, and there's one more point. There's only one other Q, point Q in P inverse P, and it has the expression X. In this case, we have X is equal to X1, Y is equal to Y1. Okay, and this is in the chart U2. So then you go through the same kind of process and you end up with this substitution. That's the only other one you don't have. Okay, so okay, now let's consider the case that so now we've studied the blow-up itself, but we want to apply this to resolve the curve singularity. So in fact, by iterating this blow-up enough times, we can resolve every plane curve, every singular equation in the plane. And you notice that in this nice case that we start with A2 and you really stay in A2, that we have these charts covering it that are like A2. Okay, so let's consider this case is a curve. Okay, so we'll assume that it's reduced. It's irreducible, for instance. Okay, so then we have C is equal to V of F for some irreducible F in our original polynomial ring K adjoin XY. Okay, and this is since the polynomial ring is a UFD, which we know thanks to Gauss. Okay, so now what we need to do if we want to resolve it, we need to have a good understanding of how F changes when we blow up. Okay, so let's suppose that we take a point P and C, and could be this point which we analyze. We can change variables, make it the origin, and we're going to define a function which is in fact evaluation on the polynomial ring. This will be equal to the maximum of n, such that F is in the maximal ideal e to the n. Okay, remember P is the maximal ideal. Okay, so then now let's take the blow up of P into X A2. Okay, and let C tilde be the strict transform of C. Okay, which we talked about. In fact, we find what this is from this construction right here. So we write F is equal to summation I plus j bigger and equal to R, Aij xi1a. Okay, and with R, it's the VPF. So some, and these Aij are all in K, and we have to have some Aij not equal to 0 with I plus j is equal to R. Okay, that's what it means. So we expand F like that. And what happens when we change the variables? I mean, when we do the blow up. Okay, so let's look in U1 is equal to the spec of K of xy over y. I forgot to clean this properly. Let me do that again. Okay, so in U1, which is the spectrum of k xy over y, what we can do then is rewrite f as being equal to summation I plus j is equal to r at x over y to the I times y to the I plus j, right? Because these are the two new coordinates. So we write it like this, and we see that this is equal to y to the r times summation I plus j is equal to r. I plus j is equal to r x over y to the I times y to the I plus j minus r. Okay, so remember that I plus j is bigger than or equal to r always. So this makes sense. And in fact, this over here is not, this is divisible by y to the r, but this isn't. So what one sees here is that this is y is equal to 0, is a local equation of E. Remember in that chart, this one. And this over here is a local equation. If I set this equal to F1 tilde, this is a local equation of the strict transform. Okay, I've pulled out everything which gets in the way. This is a nice irreducible curve here. So we have this. Okay, so one has then that this the ideal of the of this strict transform is equal to F1 tilde. So the ideal of C tilde intersect. I guess I should say not be too careless. Strictly speaking, if I look at this is just the ideal F1 tilde. So that's nice. So F1. Well, I've already written it over here. Okay. So, and one can also compute that gamma U2 I C tilde is going to be F2 tilde, where F2 tilde is the summation I plus j bigger than or equal to r a I j y over x to the j x I plus j minus r. Okay, it's just the same calculation, only switching out. Okay, so now let's check something else. See, well, what's happened? Let's look at this and see, well, did something get better or not? So let's look at this. The leading form of f is L is equal to summation I plus j is equal to r a I j x I y j. So remember, these are the terms of lowest degree, and there's a bunch of other stuff maybe up above it, but we just single that out to be the leading term. Okay, so now let's suppose that we take a point, a closed point. Q is in maps down to our point P. Then remember, there are regular parameters we just showed. There are regular parameters x1, y1, or maybe what I should say is, let me write it like this, that Q is equal to this maximal ideal, x1, y1, and we have two forms where x is equal to x1, y is equal to x1, y1 plus alpha. where alpha is in K, or the other form is x is equal to x1, y1, and y is equal to y1. That the point, there has to be this kind of expression. So in the first case, one has that the local equation of the strict transform is f over x1r. And this one is summation I plus j is equal to r aij y1 plus alpha to the j plus x1 omega for some omega. So what one does is that for the terms in here, if you make the substitution and then you pull out x1 to the r, then the x just completely vanishes and you end up getting this. And then in the higher degree terms, then, well, everything is going to be divisible by x1 to the r plus 1. You're only dividing out x1 to the r, so it'll be something like this. And then what one can say is that the first fundamental fact, okay, so one sees this, since this part is here, well, you want to know the order of this guy, right? What is the order? Well, you know that there always has to be this y1 to the r. There has to be a term in here of order less than or equal to r, right? Because this is non-zero and it's a polynomial. Every coefficient in here is less than or equal to r. Okay, so this is less than or equal to r, and if it doesn't drop, then this implies that this guy, a plus j is equal to r, aij y1 plus alpha to the j is equal to just a 0r y1 to the r. See, if there were any other terms that are non-zero than this one, then it would have to drop to be less than that, so that one can then write that the summation I plus j is equal to r a by j y1 to the j was equal to a 0r y1 minus alpha to the r, because you just substitute here, say y1 plus alpha, set that equal to y1, so y1 becomes y1 minus alpha, and then we have L is equal to a0 y minus alpha x to the r. Okay, so the leading form, that the multiplicity will never go up, and if it doesn't drop, then it has this very special form. Okay, and in the case, the remaining case is when Q, in the remaining case, is when Q an element of phi inverse P, and this is equal to it was the other case, which we did. This one was x1 is equal to, I guess I can figure out what it was. It was x is equal to x1, I guess it's y1, x1, y1, right? Because x is equal to x1, y1, y1, right? Where this is the remaining case, then one can check that, again, that the BQ of C is again less than or equal to R. You made the corresponding calculation very similar to this one, except for the fact that that roles of x and y's are reversed and alpha is equal to 0. You get from this that VQ of the strict transform is equal to R implies that the leading form is equal to AR0 x to the R. Okay, so we have these very special forms. The first thing one notices is when one blows up this multiplicity is a good invariant, that it never goes up. And if it doesn't go down, then you have some very special situation that you can detect. Okay, this leading form has this very nice simple form. Effectively, it's just in one variable, right? Like you could change variables and replace y with y minus alpha x. And again, it's just going to be in terms of one variable. Okay, so I'll stop here for today. And next time we'll start by completing the proof of resolution of surface singularities. First thing I want to do is make some comments as we did all these constructions in A2 because it's more transparent. But in fact, these calculations work in any regular local ring. So if you take any non-singular point on the surface and you take a curve passing through it, then you can blow up that point. And really these same equations appear. In fact, on the level of completion, they're exactly the same. Okay, and then after that, we'll actually give a proof of resolution that we see from this. Okay, what we'd really like is something where we can have some measure where everything gets better. Well, we've made some progress. We have this order function, this multiplicity, this V of P, that at least it doesn't get worse. If we can get it to drop, then we have won, because when it does drop, it's a positive integer which goes down by 1. So if you can get it to drop, then you keep doing the same thing, and eventually you'll get it to be 0, and the order of being, or get it to 1, sorry, and the order of being 1 is equivalent to being non-singular, being regular. Okay, so what we need to do now then is we're going to find a second invariant, which you use along with this one, which tells you that, okay, if this number drops when blowing up, then you've won. Well, let's say it doesn't. Then there's another invariant you keep track of, which is, okay, it doesn't drop, but there's another number that will drop. And if every time that you blow up, if the multiplicity doesn't drop, that number will drop by 1 more. So again, this is a positive integer, which keeps decreasing. It can't keep going down forever. Okay, so eventually you have to win and get something where the multiplicity is dropped. And that this actually philosophy is really how the starting point of other proofs of resolution of singularities, in particular the proofs in characteristic 0. So that's what we'll finish up with next meeting, which I guess is Tuesday, right? Tuesday. Yeah, next Tuesday at this time. Okay. Thank you.
What? Questions here?
Questions from the audience? From the computer? I don't think so.
No, I think,
Yeah.
Okay.
So I have a few questions. First of all, you just said, right? So the whole strategy is always creating invariants, and then you're creating some sort of maps that will prove.
Right, yeah.
So first silly question. So here you're doing in a point, right?
Yeah.
Can you guarantee that these maps might improve this, but do not destroy what you have built in other points?
Because remember that in this case, so let's just stick to this case where a curve on the surface, because it gets dramatically harder when you go beyond that. But these have the virtue that nothing changes when you blow up, except for above that point. So remember, there's this one copy of P1 in which you replace that origin with. So nothing changes at all anywhere else. So you have to, in fact, to give a global algorithm, what one has to do is observe that there's the singular points of the curve is a finite it's a Zariski closed proper subset, so it's a finite number of points. So what one does is that this algorithm here, what one does, the algorithm is, so you take the curve, you take the finite number of singular points, you blow up each one of them, which are independent things. And then I mentioned this, there's an algorithm, there's this invariant, this multiplicity, comma, something else. And that at each one, as you continue to blow up points, until everything above, you have these various chains perhaps, but eventually it'll have to end on all of them. So then that works well for curves. This very simplistic argument works well for curves, but for say for surfaces even, it's much harder because you might have a singular curve. Okay, and then the first thing you have to do is decide, well, do you blow up a point or do you blow up a curve? So the continuing the strategy, you take a singular surface in a non-singular threefold. You either blow up a point, or if you blow up a non-singular curve, blowing up the non-singular curves gives you again some ambient space, which is non-singular. You take the Strix transform. But it gets more complicated about keeping track of what's going on. And then eventually when you get to the general case, it's much more.
How optimistic are you that we will reach a solution in the future?
I don't really know. In fact, what had happened that some years ago when I was much younger, I was surprised how how everybody else seemed to be certain it was true, although the history was this long struggle to try to get it in dimension 4. But now I notice that people, the experts, seem to be less optimistic about it. That certainly our friend Vincent Cossart is much less optimistic. And when I first met him, that he was sure it was true. So, but I don't really know. You know, it may be that what I do think is that using the traditional methods. He's written this terrible thing, which is with Olivier, which is hundreds of pages long. And it's a series of these, of all kinds of ad hoc methods. And it relies on some things which are special in dimension 3. And they haven't been able to go beyond this. And it seems that the idea of, I looked at this a little bit with the ideas, okay, maybe I can give something like, simplify it and get a 20 or 30 page proof or something. And it's really, really complicated. So I don't know that. I mean, even if it's true, the complexity of the proof would be absolutely staggering. But it may be that there's, there's some, it's like, for centuries, everybody was trying to prove that that you could solve the quinic. So of course, from this point of view, perhaps this is a bad example, but somebody did solve the problem, but fairly easily using a completely different method.
Yeah.
And it may be that's the case. And this last proof you mentioned was it is a new method. So. Okay. But yeah, I mean the answer is, as far as I know, there's no contender which there's sort of a consensus of opinion by the experts that it might lead somewhere.
Maybe short words about local uniformization. The same?
I'm sorry?
About local uniformization, the same?
It seems to be the same. Yeah, that seems to be that certainly. Certainly, this seems to be the same. Yeah. And you'd have talked to some experts on this. So
yeah, I think they share the same opinion as you, more or less. Some questions? No?
Let's see if somebody here might have now. João Elder, just a curiosity, beyond the case of curves, is there some implemented in a computer characteristic 0, which does the job of resolving singularities for surfaces?
Yes, there is. And I think there's one even generally for general dimensions. The complexity is absolutely staggering. So I think it's probably been getting better. And I should remember the name of some of the people who've done this, but I can refresh my memory and say something next time. But there are algorithms, there's a number of people working on it and they're improving them. But there is sort of a hard fact, which is that, for instance, you see in this case here, every time you blow up, you get 2 new charts. So you see that quickly it grows and the complexity gets completely out of sight very quickly. So say for this situation, for the plane curves, I think there are very reasonable computer algorithms which converge. For surfaces, it's still not too terrible, but in general, it gets very complicated to try to resolve them. But yeah, there are that using Grosvenor basis techniques and everything like that, there are methods which allow you to resolve everything, and there are computer programs to do it.
Thank you. Are more questions? Are there more questions from the internet? You said thanks. So seems not to be the case. So let's thank Leo again.
Okay. Okay. Goodbye, everyone.
Goodbye, everyone here. I was afraid that I was going to run out of battery.